Hello and welcome to today's lesson 20.3 on Hubble's law. Edwin Hubble was an American astronomer and certainly really important in what he discovered, and that is V is roughly equal to h naught d, which then gave us a Hubble constant. And what he did was he used the idea of redshift to come up with the age of the universe. So that's what we'll focus the bulk of the lesson today, and we'll also mention something called the cosmological principle. So if you haven't done so already, it's really important you've looked at chapter 20.2 and you're familiar with the idea of redshift. In your book, in figure 2, in chapter 20.3, there's a nice little picture which we'll look at briefly now. So if you recall, everything is compared to what you'd see in a laboratory. So if we looked at a particular series of frequencies or wavelengths, you might get these black lines in a lab. A nearby star, what you'd see is it's slightly moved towards the red end of the spectrum. In other words, the star is moving further away. And then if you then compare that to something that's a bit further away but still nearby in comparison, so a nearby galaxy, it's even more redshifted, and a further away galaxy, so a distant galaxy, it's further away again, and a galaxy that's even further is even more redshifted. And the first thing to note is the further something away is, the much more it is redshifted. So the key thing to remember here is it's not a linear relationship. So something that's even further away has got an even greater redshift. So it's not proportional, it's not linear. So a useful website is hubblesite.org if you're interested in the Hubble telescope, which I'm hoping that you will have heard of. It's still in space now, it's well worth having a little research, and it's obviously named after Edwin Hubble. Back to the specification though. So it was in 1920 that Hubble analysed the absorption spectra of distant galaxies, and he noticed a couple of things. The vast majority, so not all, were red-shifted, and the further away the galaxy, the greater the redshift. So the further away they are, the more those black lines had moved towards the red end of the spectrum. So he then came up with a proportionality equation where V is directly proportional to D, or the proportionality symbol he called h naught, or the Hubble constant. So V roughly equals h naught d, where V is the recessional velocity and D is the distance away of the galaxy or nearby star. So I said it's the complicated bit. Some of it's easy, and you'll then need to do a little bit of maths and thinking with some unit conversions in a second. The easy bit is hopefully recognising that velocity and distance are proportional to each other, or roughly proportional. You can see there's quite a large area of doubt. We've got not all of them following that red line, and that's why we've got those squiggles between V is roughly equal to h naught d. However, they're certainly very close to being proportional. The tricky bit is focusing on our units. So distance, if you recall back a couple of lessons, parsecs or megaparsecs. So as a reminder, mega means times 10 to the 6. And we've also got kilometres per second rather than metres per second, just because of the distances involved. Notice that the scale is also not even a logarithmic scale. So using maths, we know that y equals mx plus c. On the y-axis, we've got velocity. On the x-axis, we've got distance. So our gradient is that h naught, the Hubble constant. So the units for h naught are just the gradient of the line. Kilometres per second per megaparsec. Now, a skill that you need to be able to do for your exam is to convert all of this into per second. So what I'd like you to do, please, is have a go at converting 70 kilometers per second per megaparsec into just the unit of per second. So you've got a speed or a velocity divided by a distance. So you'll be familiar with the units. So it would normally be meters per second divided by meters. So we're looking for a unit of s to the minus 1. So think about what you know about kilometers. Think about what you know about seconds. That bit's the straightforward part. And look back at what you know about megaparsecs and its conversion. So what you're looking to do is convert these distances into meters, and remember there's a 70, and give an answer to s to the minus 1. I realise it might sound a little bit complicated, but just give it a go, see what happens. So the answer that you're looking for is 2.3 times 10 to the minus 18 per second. So before we look at what does that even mean, let's just go through how to get there. So first of all, we'll start with the 70 kilometres. So hopefully you'll recognise that 70 kilometres is equal to 70 times 10 to the 3 metres. So park that for a second. You also know that 1 parsec is 3.1 times 10 to the 16 metres, and that can be found in the data booklet. So 1 megaparsec is 3.1 times 10 to the 22. So all we do is speed divided by distance. So our speed or velocity is 70 times 10 to the 3. And that's then divided by, because it's a per megaparsec, 3.1 times 10 to the 22. The metres will cancel through, leaving that s to the minus 1 as the unit, and that gives us 2.3 times 10 to the minus 18 per second. So that's Hubble's constant. Now, the actual value isn't 70 kilometres per second per megaparsec. The actual value is roughly 68, which is taken from the gradient where the units here are kilometres per second and the distance is measured in megaparsecs. So there's two ways of talking about Hubble's constant. One is per second and one is per kilometre per megaparsec, or kilometre per second per megaparsec. So now on to the question that the dog's asking. What does that even mean? So what I'd like you to do is have a think. What does the Hubble value here tell us? So what does it mean to be 70 kilometres per megaparsec? So have a little think, and when you're ready, resume by pressing play. So hopefully you've given that a thought. The way I like to think of it is we've got Earth somewhere like that, and then 1 megaparsec away we've got a distant star, and that's receding, travelling away from us at 70 kilometres per second. But then if we travel an extra megaparsec, so 2 megaparsecs away, then what Hubble realised was it was travelling faster at 140 kilometres per megaparsec. And hopefully you've got the idea. At 3 megaparsecs away, it's travelling at 210 kilometres per second away. So in other words, the further away something is, the much faster it's travelling away from us. The closer something is, the much slower in comparison it's travelling away from us. So for every megaparsec away, the galaxy travels an additional 70 kilometres per second away from us. So Hubble's law is absolutely key evidence for the Big Bang Theory, and we'll look at that again next lesson. But it's part of the model of the expanding universe. the idea that things are still moving away from us and the universe is getting larger. And it's the model that's most widely accepted because nearly all galaxies we can see are redshifted and are therefore moving away from us. Now, the other part of the question is, what does that even tell us? Is the reason why we sometimes write it as seconds to the minus 1. Now, you've also seen seconds to the minus 1 as the unit of hertz, as frequency, but that isn't actually very helpful right now. However, if we think about what s to the minus 1 means, it means 1 over s, or 1 over time. So if we now inverse 1 over s to the minus 1, that actually gives us an amount in seconds. So if we do 1 over 2.3 times 10 to the minus 18, 1 divided by 2.3 times 10 to the minus 18, that gives us an answer of 4.35 times 10 to the 17 seconds. And what that tells us is the age of our universe. Clever, eh? So we'll look now at some past paper questions on this topic. We'll go through each part question, and then between each one there'll be time for you to have a go just by you pressing pause. So I've got here a question that says state Hubble's law. So at this point, give that one a go. So on a piece of paper that you have near you, just write down what Hubble's law is, and then when you've done it, we'll go through the answer. So the answer for this one is the recessional speed or velocity of a galaxy is proportional to its distance from us. The idea that v is proportional to d, but you needed to use the word galaxy. For part B, the redshift of a specific spectral line in the spectrum of a galaxy can be used to determine its recessional velocity v. The fractional change z in the wavelength of a spectral line is given by the equation z equals v over c, where c is the speed of light in a vacuum. Now, if you recall, certainly in some of the sheets that you should have read, not necessarily in the last video, but that is the same as delta lambda over lambda, which is the same as delta frequency over frequency. So the table of figure 11.1 shows data from some of our closest galaxies. The distance of the galaxy from the Earth is d. Complete the table by determining v and d for the galaxy Messier 109. So give that a go, and when you're ready, press play for me to go through the answer. So first thing to do, if it were me, would be to write down the equation. Realise that c is a constant, so we know that one, 3 times 10 to the 8. So we're trying to find v, so that's just z multiplied by c. So z is 3.38, and then we need to remember times 10 to the minus 3. And then we multiply that by 3 times 10 to the 8. So 3.38 times 10 to the minus 3, multiplied by 3 times 10 to the 8. And that gives us 1014,000, or 1010 times 10 to the 3, to 3 significant figures. To find d, it might take a little bit more thinking outside the box, but we know that v is proportional to d, and the clue is from the first question. We're probably going to have to use something to do about Hubble's law. So we've got a couple of extra values for v and d from other galaxies. So if I do 336 times 10 to the 3 and divide that by 1.5 times 10 to the 23, I then get a value for h0 as 2.24 times 10 to the minus 18. So I can now translate that as part of my answer for D. So V equals h0 D, or D equals V over h0. My value for V I've already got. So 1010 times 10 to the 3 divided by my answer to the previous part, So the value for D is 4.51 times 10 to the 23. So 4.51 and 1010. For the next part, figure 11.2 shows the data for the first 4 galaxies plotted on a V against D graph. So the best thing that I suggest you do to start with is just double check the units, because you've seen them as kilometres per second and megaparsecs, and in this case it's already converted into the standard units for you, but we still have got some times 10 to the 23 and times 10 to the 3. So use figure 11.2 to determine the age of the universe in years, and then it's given us a unit here for how many seconds are in a year. So give that one a go, and when you're ready, resume by pressing play. So hopefully you've given this one a go, and the first thing I would do would be to draw a straight line, and it should be through the origin. There's not many topics in physics where you're allowed to aim straight for the origin, but this is definitely one of them. And then once you've got your line, you can then work out the gradient from it. So as normal, you would need to draw your triangle as large as possible, like so. So we've got 3.1 by the looks of it, 3.1, 3.2, 3.3, 4 and 5. And then that's down to 0. And then along the top, that looks like on here, it's about there. So that's 680. So we're going to want delta y over delta x. So the change in y is 680, and the change in x, because we're referring everything down to 0, is 3.1. But we need to remember it's 680 times 10 to the 3, and it's 3.1 times 10 to the 23. So if we put that into a calculator, that gives us 2.19 times 10 to the minus 18 seconds to the minus 1. So because it's s to the minus 1, we then need to inverse it by doing 1 divided by that value, which then gives 4.56 times 10 to the 17 seconds. And we know that 1 year is 3.16 times 10 to the 7. So if we divide that through by 3.16 times 10 to the 7, that will give us the number of years, which works out to be 1.44 times 10 to the 10 years. Now for part C, we won't do that question now, because if you read it, you'll see that we haven't yet covered it. It comes on the next part of the course. On to the last bit of today's lesson, and that's, as I said at the start, the cosmological principle. Now, with all things in physics, we have to assume things. We have to make an assumption about lots of things. And when we look at space, we call it the cosmological principle. And it's the assumption that when viewed on a large enough scale, the universe is said to be homogeneous and isotropic, as well as all of the laws of physics that we understand on Earth happening everywhere. They're universal. So there's some keywords there to be able to distinguish against, and I've written them just there for you to have a read through, but it's always going to be worthwhile looking at other sources as well, just to help you remember the difference between the three of them. So homogeneous, the idea that matter is distributed uniformly across the universe, just like Lego brick blocks. So that's the picture that I've got there in the orangey yellow colour. Density is uniform. Now we know that actually density isn't uniform because we've got the solar system, we've got the sun, we've then got all the planets, but in between we've got a vacuum. But when we look on a large enough scale, it's roughly uniform. There are the same structures and that are seen everywhere. So we know there's galaxies everywhere. So on a large enough scale, we'd call it homogeneous, that matter is distributed uniformly. The other word, and they're quite similar really, is isotropic. So whatever direction you look at, it looks the same. So the universe looks the same in all directions to every single observer. And the other assumption here is, and it's quite hard to get your head around, there's no centre in the universe and there's no edge to the universe. And I think people like to think about it being a balloon and the balloon expanding. But of course, the balloon has a middle and it has size, it has an edge, and we can't see the universe like that. So it's isotropic, looks the same in all directions, and there's no centre or edge to it. The universal laws of physics, so that's just, we know that, we've got gravity on Earth, and if we drop a ball, it's going to fall. And if we go to a different planet, we'd expect the same thing to happen. Likewise, all the other equations that we've got, everything that we've learnt, we can hopefully and assumedly apply everywhere in the universe. So what we see on Earth, we would say happens everywhere. So for homework, I'd like you to have a go, please, at the summary questions. And I've also got you some other reading to look through, which I'll attach to show my homework. And to hand in, please, I have a couple of past paper questions similar to the one that we went through earlier to hand in. And please, when you hand them in, can you make sure they're sent in as PDF files if you would like any feedback. So if you have any further questions, please do get back to me and I'll do my best to help and hopefully see you soon.